All right, we are here for our final particular set of notes for this particular chapter here. So let's get going. This is Newton's laws. Now this one is a pretty long one, but just strap in, we got this. All right, so let's begin with force. So force is a capital F. It's when there is a push or pull on one object when it exerts on another. Let me rephrase that. Push or pull one object exerts on another. There we go. It's measured in newtons, and so that's a capital N. 1 Newton is equal to 1 kilogram times meters per second squared. Forces can cause a change in an object's motion. More than one force can act on an object at one time. So then a net force is the combining of forces when two or more forces act on an object. So if we have a force on this stack of books, 2 newtons to the left, and we have a force that's pushing 2 newtons to the right, 5 newtons to the left, our net force will be 3N to the left because we subtract 5 minus 2, and to the left because to the left has a stronger force. We also can have forces that are balanced and unbalanced. So let's talk about balanced first. So balanced forces are those that are equal in size and opposite in direction. So they do not cause a change in motion because the net force on the object is 0. So let's take our stack of books, for example, here. Let's say someone is pushing towards the books at 4 newtons to the right, but then you have someone else also pushing 4 newtons to the left. So 4 minus 4 here is 0. So our net force is 0. We have a balanced force, and they're going in opposite directions. Okay, let's talk about unbalanced forces. So these are forces that are not equal in size and opposite in direction. The net force causes the object to move in the direction of the force. So let's say we're pushing the stack of books again 2 newtons to the right, and then we have somebody else come and help you to push it 7 newtons to the right, and then somebody comes in and pushes 3 newtons to the left. So what you're going to do is you're going to add this side together. So 7 plus 2 is 9. So technically you're moving 9 newtons to the right. So 9 minus 3 is 6 newtons to the right because the right has the greater force. Let's talk about Newton's first law. So Sir Isaac Newton came up with 3 laws in 1687 that describe how forces affect an object's motion. So Newton's first law means an object will move at a constant velocity until net force acts on it. Or an object in motion will stay in motion, or an object at rest will stay at rest unless a force acts upon it. So an example here would be bowling. The pins don't move and the ball doesn't move until something and someone forces them to. So the ball has to be rolled down the lane. The pins don't move until the ball hits the pins. Newton's first law is also known as the law of inertia, and inertia is the tendency of an object to resist a change in motion. So you guys probably have heard inertia in like the Bill Nye theme song because this is where he gets it from. All right, the more mass an object has, the more inertia it has. So for example, when you slam on the brakes in a car, your body actually still flies forward because it wants to stay in motion like it was before you braked. This is why you wear your seatbelt. And this is why a lot of seatbelts have locks, especially when you get into a car accident, especially one that you total a vehicle where your airbag deploys, because you're less likely to have a broken nose this way when your seatbelt does its job. All right, so what kinds of forces change an object's motion? Friction is the resistance to motion when two objects are in contact with one another. There's air resistance, which is resistance on an object feels when traveling through the air. And then you also have gravity, which is the attraction two objects have on one another. This force of gravity pulls us actually towards Earth. That's why we're able to stay on Earth and not just do a floaty dance out in space. So let's break it down. Let's start with friction. So there are 3 factors that friction depends on. Number 1, the rougher the surface, the greater the friction. So rougher surfaces actually have greater microwelds, which are microscopic bumps on the surface that causes friction, which increases the resistance between the objects. Kind of makes sense if you think about it, just because of we have been around rougher surfaces like sandpaper and that kind of thing, and sandpaper is much harder to move across the surface or across each other than it is like, say, your hands or even 2 pieces of wax paper or anything like that. The greater the force pushing the two objects together, the greater the friction. So it increases the opposition of the microwells between the objects. So the harder you push two things together, the harder it is to kind of move them across each other, which means the greater the friction. Also, third and last one is the greater the surface area of the two objects touching, the greater the friction. So the increase in contact between the two objects does cause that increase in friction. There are three types of friction. Our first one is static friction. So this is a force between two surfaces that are not moving past each other. The easiest way to think of this right now, this picture shows a box that's just sitting on the floor. Between the floor and the box, there is static friction because there's no movement there. It's the same thing if you sit your butt in a chair. There's static friction between your butt and the chair. Sliding friction is a force between two surfaces that are sliding past each other. So let's take our box example again. Our box is actually moving now across the floor. That'd be a sliding friction. And then finally, we have rolling friction. So this is a force between rolling object and the surface it rolls on. So this is now a cylinder on top of a floor and it's rolling. So there's rolling friction, which causes a rolling motion. Now let's go ahead and talk about air resistance or drag or friction in the air. This is determined by things like speed. So the greater the speed, the greater the resistance. Size, the larger the object, the greater the resistance. And shape, the flatter the object, the greater the resistance. So then we have to talk about the law of universal gravitation before we jump into gravity. So this means that any two masses that exert an attractive force in each other, this depends on things like the mass. So the greater the mass, the greater the gravitational attraction. So these two circles here are example for mass. These two circles right here are same size and they're actually attracted to each other because they're the same size. But if you take that size of a shape and a bigger round shape, they'd be even faster and more attracted to each other gravitationally. It also depends on distance. So the lower the distance, the greater the gravitational attraction. So these two circles are super far away, so their gravitational attraction is not that high. But you take those same size shapes and you put them closer together and their gravitational attraction actually increases. Okay, so gravity is the attraction to Earth that pulls objects in the air downwards. It's why here on Earth we're able to skydive. This force causes all falling objects to have an acceleration due to gravity of 9.8 meters per second squared. That is regardless of mass and ignoring air resistance. So obviously air resistance is a thing when you go skydiving, but no matter your mass, no matter how big or small you are, you're still going to fall at 9.8 meters per second squared. So let's go ahead and talk about terminal velocity then. This is a term that a lot of people hear about when they actually do go skydiving. It's the maximum velocity a falling object will reach, and it occurs when the force of gravity and air resistance become balanced. So that's that nice part where you kind of just meet in the middle. You're kind of still floating down, but now the forces acting above you and below you are working simultaneously and at the same time. So as you are going down, the force of gravity pulls you down, but air resistance opposes it in the opposite direction like that. So your net force here is 0. Therefore, you have no acceleration when you're dropping out of the sky. Isn't that crazy? So humans do this actually at 55 meters per second. Notice this is not acceleration. This is just the speed. We fall out of the sky 55 meters per second or 118.06 miles per hour. That's insane. All right, so let's talk about Newton's second law here. So how do motion and force relate? Newton's second law states that a net force acting on an object causes the object to accelerate in the direction of the net force. So the greater the mass, the greater the force needed to accelerate it. So the greater the net force, the greater the acceleration. So the example I have here is a croquet ball and a croquet stick. So the ball will accelerate in the direction of the net force the mallet applies. That's what it's called, a mallet. So the greater the force applied, the faster the ball will move. So it's the same kind of thing. Newton's second law really does apply to things like golf. They use this thought process all the time in golf. And then we can summarize it actually in an equation. That's F is equal to ma, where F is force, it's measured in newtons. Mass is m, which is measured in kilograms. And then acceleration is a, which is measured in meters per second squared. So for example, we have our first example here. You are pushing a friend on a sled. You push with the force of 40 newtons. Your friend and the sled together have a mass of 80 kilograms. Ignoring friction, what is the acceleration of your friend on the sled? Oop, there we go. So our force is 40 newtons. Our mass is 80 kilograms. We're looking for acceleration here. We have our equation of force is equal to ma. We need to get rid of mass on the right-hand side because we're searching for acceleration. So you'll divide each side by m. So our new equation looks like this. And we're going to do 40 newtons divided by 80 kilograms. And that gives us a speed of 0.5 meters per second squared. So then we have to go into talking about weight versus mass. I know we've kind of talked about this a couple of times throughout the school year, but I want to reiterate it again. Mass is the amount of matter in an object, and weight is the force of gravity on an object. So when you're when you're told to step on a scale at a doctor's office, they're actually taking your mass rather than your weight. If it was by your weight, they'd be using a different type of scale. This means that your weight can actually change based on location. So the further from Earth you are, the lower your weight, meaning further out in the solar system. The closer you are to the sun, the bigger of a weight you would have. So on the moon, your weight would actually be 1/6 of what it is now. It also doesn't have any gravity on it, so that also helps. If you could be on another planet, your weight would change based on the gravity of that planet, which is true. So on Jupiter, your weight would be over twice as much as it is now because Jupiter is larger. So we have to think about too the mass versus distance type of thing. So it kind of depends on the planet, but most of the time, the farther out you get, the less you would weigh. But it also depends on size. Jupiter and Saturn are huge planets, so compared to Earth and Mars. So of course, we would weigh more on those two planets. So diving deeper into weight here, again, weight is the force of gravity on an object. Because it is a force, you can actually calculate weight using F is equal to ma, so kind of nice. So when we're finding weight, your acceleration due to gravity is always 9.8 meters per second squared, so that's kind of nice. So for this example, we're going to find the weight of a suitcase that has a mass of 42 kilograms, which is awesome. We already have our acceleration, we have our mass, which is super nice. So F is equal to ma. So 42 times 9.8 gives us 411.6 newtons. All right, Newton's third law. Newton's third law, this one is the one that a lot of people know about because it's an easy one to remember. It's every action has an equal and opposite reaction. So when one object exerts a force on a second object, the second one exerts a force on the first one that is equal in size and opposite in direction. The easiest thing to think of is a trampoline. So if you ever have owned a trampoline and you started jumping on it, the trampoline stretches, and it's because that stretch, when it comes back, is coming back at you with the same force you exerted on it, and it's opposite in the direction of what you actually did. Just like I just said for this example. So we have the law of conservation of momentum when it comes to the Newton's third law. Momentum is a lowercase p. It's mass in motion. We use this a lot in football. Momentum does help football players to with tackles and that kind of thing. We can solve for it. P is momentum, like we've said. That's measured in kilograms times meters per second. Mass is m. It's measured in kilograms. And then velocity is v, and that's measured in meters per second. All moving objects have momentum. And momentum is transferred between objects in a collision, which is kind of interesting and something you may not think about, but it totally happens. That's why, when you watch football, sometimes those hits can be super brutal and you could hear them because the person that's doing the tackling has come at the other person with such a force and such a momentum that it causes this huge collision. So they transfer their momentum to the other person. So sometimes you can get some really sick looking hits. So for example, what is the momentum of a car with a mass of 1,300 kilograms traveling at a speed of 28 meters per second? So we're looking for momentum. We have a mass. We have our velocity. We're going to use this equation. So we're going to go ahead and plug that in. 1,300 times 28 gives us 36,400 kilograms times meters per second. Now, the law of conservation of momentum can also be talked about when we talk about collisions. So in a collision, because the forces acting on two objects are equal and opposite, the transfer of momentum must be the same. So according to the law of conservation of momentum, Momentum is never created or destroyed. In a collision, it's only transferred. So you guys have probably heard this before because this is a law of conservation of mass. This is a law of conservation of literally any law of conservation we've talked about this year. So for example, ball number 1 is rolling 11 meters per second directly toward a 0.17 kilogram ball at rest. During the collision, ball number 1 stops and ball number 2 is launched forward at 9 meters per second. What is the mass of ball number 1? So we have to think of about the law of conservation of momentum. Okay, matter cannot be created or destroyed. Momentum cannot be created or destroyed, just transferred. So this is ball number 1. We're looking for its mass. We have a velocity of 11 meters per second, and this is our mass of our ball that was at rest. This is ball number 2, and this is a velocity in which it moved to the right. 9 meters per second. So this is actually a two-part problem here. So we're looking for, we don't have P1, we don't have M1, we do have V1. So that's kind of nice. We don't have P2, but we do have M2 and we do have V2. So mass 2 and velocity 2. So we're actually going to solve the second velocity first because once we find the momentum of P2, P1 is equal to P2 due to the law of conservation of momentum. So P2 is 0.17 times 9, and that gives us 1.53 kilograms times meters per second. So since P2 is equal to P1, we can go ahead and figure out, we're trying to find mass. So we already have our V1. You're going to divide each side by V1, and we're going to end up with a new equation that looks like this to find your mass. So 1.53 divided by 11 meters per second, we find our mass at 0.14 kilograms. So this is a lengthy problem, but it's not too terrible. If you have any questions, let me know.